One example for the Doppler shift is what we call shockwaves. That's when an object's speed exceeds the speed of sound or the speed of the wave that it's producing. So in that case, it will produce what we call shock waveforms. For example, let's look at this. If the source is not moving and it's producing waves, the wave fronts are going to make concentric circles. So this is the first one produced. This is the one that was produced after one period, after two periods, after a third period. Now, if the source is moving, this is what we saw with the Doppler effect. The first wave that was produced when the source was here is here, that wave front. But the second one is here. The second one was produced after the source had moved a little bit. So it is centered at another place than the original wave front. The last one is centered even further out. So the waves compact up front and expand in the back. And that's what we have seen. Now, what if the source moves exactly at the same speed as the wave? So it's somewhat like this, but in this case, all the wave fronts are going to be compressed here in one location. Since the source is moving at the same speed, the wave front is not going to be able to move away from the source. So the source and the wave front are following each other. Now, we get shock waves when the source actually moves faster than the wave. In that case, this one is the original wave front. When the second one was produced, the wave is going to be moving even further. For example, this last one here. This one was produced, but by the time the wave front reached here, since the source is moving faster, the source is ahead. So because of that, these wave fronts are going to meet up here in a sort of a cone that we call the Shockwave Cone. Okay, let's look at it as part of a simulation. Okay, so we have the simulation. Our airplane is going to start here. Look at the window here and the apple here. And as our wave moves, look at the shock wave being formed since the airplane is moving faster than the speed of sound. You see, it dropped both of our window and our apple. Let's review it again. So this is the Shockwave Cone. Now, let's analyze that a little bit. Since the source moves with a speed Vs, at a time t, it's going to move a distance that's equal to Vs times t. That's represented in red here. Now, however, for that same amount of time, the first wave front, or the wave front produced when the source was here, had moved a distance, what's represented in green here, Vw, the velocity of the wave, times t. Now consider this right angle triangle here. The angle for that triangle is a measure of the width of the shock wave cone. Now that angle, since this side is the largest side of that right angle triangle, so this side is the hypotenuse, this side is the opposite to the angle, so the sine of the angle is given by this. Vwt over Vst. The t's cancel out and we are left with Vw over Vs. So we can get the angle by doing the inverse sine of the ratio of the velocities.